So much, Duncan. It's good to be here. So just progress on the next slide, and I cannot control it for some reason. There you go. So as Duncan mentioned, I'm the chair of ESIG High Inverter-Based Resource Penetration Task Force. And within the task force, we are looking at emerging issues with operating high levels of inverter-based resources. And currently we are working on a white paper that's on the role of grid forming technology to enable energy system integration. And so here you can see an outline of the paper. I don't go through it. We're currently working on a draft, and next meeting we have is on November 17, and we'll review what we have up to date. And if you are an ESIG member, you can join the group meeting. So it's open to all ESIG members. And so for today's presentation, I'll focus on international project references for grid forming applications and also experiences with interconnection requirements of grid forming resources. So these are two subsections in the white paper. And I also have done this or slightly similar presentation in May for GPST and ESIG webinar. So if you heard parts of it, I apologize for repetition. So all of the materials in this presentation came from somebody else's work. So I have some people acknowledged here, this is based on their work and their papers, what I was able to find online or from resources they sent to me directly. So just to set the stage, and I think in the previous presentations, we already talked about that, what's grid forming, what's grid following. And I feel like we'll continue talking about it for the rest of this project, but this is definition that we have in the white paper right now. So grid following resources, that's what we currently have. And they rely on fast synchronization with external grid, and therefore they are termed grid following. They tightly control the active and reactive current outputs. And if these inverters are not able to synchronize during grid events, then they are unable to maintain controlled and stable output. Grid forming inverters, their primarily objective is to maintain internal voltage phasor. When grid forming controls are applied in bulk supply system when they are connected to bulk supply grid, the voltage phasor is held constant in subtransient transient time frame. And this allows inverter-based resource to immediately respond to changes in external system and provide stability and control during challenging network conditions. And this phasor also must be controlled to maintain synchronization with other devices on the grid and control active and reactive currents to support the grid. When grid forming resources are applied in non-BPS connected applications, so for example, during black start or in microgrids, this synchronization functionality is removed or limited, and voltage phasor may be held relatively constant over time. And this allows plant to operate electrical island and define its frequency. As you already heard, I think during a couple of previous webinars, there are variations of how grid forming controls and grid following controls can be implemented, and they both are subject to physical equipment constraints, and including voltage and current limits and mechanical equipment constraints, for example, in wind turbine generators. So you probably have seen this figure before, and I've been talking about this a number of times. I think we're still there, though we started chipping on this circle and solving some of the issues. So basically the problem is right now some systems starting to face high levels of inverter-based resource penetration at certain times. Now we have grid forming technology developing and research is going on. There are some real life applications, as you'll be able to see, but system operators are still finding it challenging to set exact requirements for what these resources are supposed to do. And the reason is that we are not fully understanding what is possible. And so in the absence of requirements or any kind of market incentives, developers are only going for for what's required or what's incentivized. So they're still building grid following inverters, even say for battery applications where grid forming could be probably more easily implemented compared to other applications. So what it leads to, we are ending up with more and more grid following resources on the grid. System operators are applying constraints. So for example, constraints on transmission interfaces to limit production of these resources from weak grid areas. And that leaves, that becomes more difficult to connect further inverter-based resources to the grid. And that results in shrinking markets for manufacturers. And on the other hand, manufacturers don't have clear specifications of what grid forming inverters are supposed to do to help the grid. And so the solutions so far have been these pilot projects in the field. And on the other hand, some operators started producing draft grid requirements for grid forming inverters. But the challenge still is that there is lack of standardizations and there is lack of understanding of capabilities as well as possible adverse impacts. And there is still lack of market incentives and other drivers for developers to develop this grid forming inverters. So there is a handful of pilots around the world. As I said, I presented on this in May. I tried to look if there is some more, and I only found just a few more that I tried to add in this presentation. So there is a number of battery storage, grid forming battery storage in microgrids and also used for black start application. There is grid forming battery storage in island of St. Eustatius, Darsalok wind farm, where a pilot project was ran for a period of time where wind turbines were operated as in grid forming mode. And then this next one is a one I just recently heard about, and that's Mackinac back-to-back voltage source converter that's used for flow control, and type of grid forming is used there as well, and we can discuss if it is or is not grid forming. Then there is Dalrymple battery storage project in South Australia, Hornsdale, again in South Australia, and then I'll talk about briefly two more grid forming projects underway in Australia. And then I'll switch gears a little bit and talk about drivers for grid forming developments in Australia. And then, as I mentioned, there are some system operators that are already developing requirements for grid forming inverters. And so I'll talk a little bit about what National Grid in Great Britain is doing about that. All right. So the first one is GE's grid forming applications for batteries. The first two projects are relatively old. You see it's before 2000s even. These two projects are basically for microgrid. The first one is true microgrid, just powering a small community in Alaska. And the second one, Vernon, is to increase reliability for industrial sites. So basically when industrial site is disconnected from the rest of the grid forming battery will run it in island mode and therefore increase the reliability of supply to that industrial site. Similar one is this Imperial Irrigation District project. It's 30 megawatt grid forming battery. It can run in microgrid application, so like island application, and it also can do black start. And then the rest of the two other projects, they're providing black starts for simple cycle heavy duty gas turbines. This is where diesel or some kind of other generation could have been used, but they were under environmental constraints, and so they were looking for environmentally friendly solutions and went for battery. So battery will start a gas turbine, and then gas turbine will act as a black start resource for the rest of the grid where it's connected, and so it could qualify as a black start resource. What's interesting about this, it didn't require a lot of changes in existing controls, so it was relatively easy to implement, and they use soft start to reduce inrush currents during energization. And then at the bottom here, there is a project mentioned. This is DOE funded CETO project on advanced grid forming inverter controls that I believe NREL and GE are co-leading. And I think that that project may be relevant for UNIFI as well to tap into. All right, the next is microgrid example. SMA actually implemented this application in a number of islands, I believe, but this one is where you can find most of information, more widely publicized. So this island has 2.3 megawatt peak load and 14 gigawatt hours yearly energy consumption, has 9 diesel gensets and 4 megawatts of PVs, and then in later stage, 1 megawatt battery in grid following mode was added, and then 2 more batteries in grid forming mode were added. And so the plant controller can send start and stop signals to gensets. It does frequency control, voltage control when gensets are not in operation, and it can transfer frequency and voltage control to gensets when the gensets are running. It does load distribution between 2 parallel grid forming units, and it doesn't require any extra communication. So the units just share load automatically. They did test in diesel off mode when it was operated. The entire island was operated 100% on storage and solar. And then when it went into operation, now they regularly operate in diesel off mode during daytime when it's sunny and they have enough storage. It can seamlessly and immediately transfer load during generation contingency, and they experience simultaneous loss of all gensets during peak load conditions in real time in operations. A frequency dip 0.6 hertz, and they were able to restore frequency back to normal within 3 seconds without any load shedding. It has also been tested during right-through conditions in real-time operations. So this is kind of a successful example of microgrid operation with grid forming inverters. Right, this is, I think that's probably the largest test that's available to date for grid forming inverters connected to bulk supply system. So this one had 23 direct drive full converter wind turbines, total capacity of 69 megawatts, and they were retrofitted, or the controls were changed to operate in grid forming mode for 6 weeks in 2019, and that was done in Scotland. They were operated in virtual synchronous machine mode, tested various inertia constants, and you can see numbers here on the slide. They experienced 6 large under frequency events just from grid conditions. It wasn't induced frequency event, and then they also induced a large frequency event because the ones experienced during the test were not large enough. And during those tests, the wind farm was able to perform as expected for the setting of inertia constant that they were testing at the time. There were no significant grid voltage phase jumps during the test, and so the largest one was 0.2 degrees. Right. They didn't experience any wind turbine trips, overpower, overcurrent trips during grid events. The limitations they were able to point out during the tests is turbine's ability to respond may be affected by wind speed if the wind speed is declining during response. So for example, if it's providing inertial or frequency response and the wind speed is declining at the same time, the response is less than what would be expected for inertia constant setting that they had. And also inertia, the wind turbine's ability to respond at low or zero power output is extremely low. And so on the same wind farm, they've actually also tested islanded and black start operation in August to October 2020. They were able to show that this wind farm can operate autonomously in island mode with a small number of wind turbines operated in grid forming mode. So what they basically tested, they tried going from all wind turbines operating in grid forming mode, and they were able to go down to, if I remember correctly, as far down as one wind turbines, one or two grid turbines in grid forming mode. And initially turbines were just tested to power up auxiliaries within the wind farm, but then they also connected 7 MVA load bank and tested it, fitting small load connected to the wind farm. So these tests were also all successful. And then for the Black Start test, they actually equipped 4 wind turbines with small diesel generators. So they could have used batteries here as well to power up turbine auxiliaries, but it would have taken longer time and to figure out control systems. So as a proof of concept, they use small diesel here, and just for comparison, the diesel is 125 kVA, and each wind turbine is 3.4 MVA size. So it's small compared to turbine size. And so these 4 diesels would power up wind turbine auxiliaries, and then these 4 turbines were in grid forming mode and were able to energize the entire wind farm. And then 33 to 132 kV transformer, and 132 to 75 kV transformer, and all the way to the breaker, 275 line breaker that connects the wind farm to the rest of the grid. And then they stopped the test at that point, so basically because that was meant to be just that they tested. And the test was successful, and they also used soft start to reduce inrush currents into transformers. Right. So this is the one I just recently heard about. To be fair, two days ago, I heard about this project. So this project built by Hitachi ABB, it's 200 megawatt bidirectional back-to-back HVDC light converter station, was commissioned in 2014 to help control power flow and enhance grid stability in the, I believe it's in MISO footprint. So basically this, can I get the, I'm not sure how to get the laser point, but never mind. So if you look at the top figure here, the upper
pointer options, Julia, right click, pointer options.
Pointer options, I can see it. Thanks, Deepak. So this upper side of the peninsula here, it's called up. Michigan Peninsula, and then the lower side is here. And so the lower side has much stronger grid, and the upper side has very little population, weak grid conditions. And so this back-to-back HVDC converter was placed between these two in line with pre-existing 138 kV AC cable double circuit. And so for the converter, HVDC light technology was selected because it's provided better voltage and reactive control, stability for weak grid conditions, can provide power oscillation damping, governor-like frequency control, supports island operation, and has black start capability. Keep in mind, all of that is using the south side as an energy buffer. So it needs to pull energy from the south side to provide all the services to the upper part of the grid, if in, say, an islanded operation or for black start or during governor-like response. And so because south side converter was connected to strong grid, they went for current control strategy, whereas in north side converter, because it connects into extremely weak grid, they went for what they call in a paper phasor voltage control, and it's developed to directly control converters' internal AC voltage, amplitude, and phase. And I think, to me, and based on the functionalities that are described here, that sounds like grid forming to me, that although they don't call it grid forming in the papers, and I think because that term probably didn't exist at the time. I was surprised how little it was talked. I haven't heard about this project before, and I was surprised why, say, ABB doesn't advertise more this project, as now we are getting more interest in grid forming. And one of the reasons I could think about is maybe because it's a transmission asset, and it's kind of, it's not a resource, it's not viewed as a resource, but I think maybe we can learn something from operational experiences. Maybe they had some issues, so I intend to follow up on this one and see if we can learn more from the operation of this project. So the next one is also from Hitachi ABB. It's energy storage, grid forming energy storage project in South Australia. This is the largest, if you don't count the previous one, this is the largest grid connected grid forming project, but this is with the battery, so it's a resource. It's 30 MVA and it's 8 megawatt hours storage. It's operating as virtual synchronous machine. Right, it was commissioned 2018. It's near the end of the long transmission line that connects this part of the grid to the rest of South Australian grid. It fits small load here, and towards the end of this radio feeder, there is also 91 megawatt wind farm. And so what this project can do, it's if this line trips, then the project can power up this island, and the wind farm is in grid following mode, the battery is in grid forming mode, and it can still maintain supply to this load without interruptions. And so in the first 6 months of operation, they were able to reduce loss of supply in this area from 8 hours to 30 minutes. Right. So this project is designed to provide a number of services. It can provide an inertial response of 200 megawatt seconds. The inertial response is with configurable magnitude and slope. So it can be changed, something that cannot be done for, say, synchronous machine, because it's determined by its physical parameters. And that inertial response allows to reduce rate of change of frequency after loss of grid or generation. And yeah, it's different from fast frequency response because it doesn't require any external measurement for response. It supports system strengths in the area, can operate in very low short circuit ratio. It has a short-term fault current overload. It's up to 2 per units for 2 seconds. As I said, can support island operation. I think what's interesting here is that inertial response is set such a way that when interconnection to the rest of the grid trips, frequency increases so much that it trips rooftop PVs in the area, and that's done specifically to avoid overgeneration conditions in an island, because the wind turbine may be generating, full amount, and the load is not as high for an island to consume all of it. So before a wind turbine can regulate its output down, it initially trips some rooftop solar in the area. It has black start capability, so it can start a local 33 kV distribution grid and 8 megawatt demand. And then voltage is ramped up slowly to prevent inrush currents. Again, the soft start is used, and then it's connected with the rest of the grid. And it also participates in this system integrity protection scheme. So this is like special protection scheme used in South Australia. It's when an AC interconnector from South Australia to the rest of the grid trips, then the battery can respond within 250 milliseconds and provide frequency support. Right. And one thing to mention here, I've read in the paper that the only services that are monetized for this project is participation in energy market, ancillary services market, and inertia. So all other services, they are kind of just part of the test, and they are not monetized and are as a proof of concept. This project received some support from National Renewable Energy Association in Australia. So the next project is Tesla Hornsday battery. So this battery was initially designed as grid following. It was installed in 2017 as 100 megawatt battery, and then was expanded to 150 megawatt in 2020. And currently Tesla, well, it's currently as of May, because I wasn't able to find updated information on this. In May, they were testing 2 inverters to operate in what Tesla calls virtual machine mode. And so it's this virtual machine mode is like a control block that's running parallel with conventional grid following component, and under stable system conditions, it behaves like grid forming inverter. And during disturbances, it can produce active response proportional to rate of change of frequency. So it's basically instantaneously injects active power into the grid. And this was real life tested in a frequency event at the end of May, when they had an explosion at coal power plants, and it also resulted in trips of a couple of neighboring units. And so here you can see on the upper chart, you can see overall response from the battery, and battery participates in frequency control services. So it's expected to provide fast frequency to primary frequency response. And so here you can see as frequency starts declining, the entire plant starts providing something that looks like regular frequency response, and it peaks about the same time as nadir hits in frequency. And frequency is in purple here, and response from the plant is in orange. Whereas at the bottom, what you can see is a response from just those 2 inverters that they were testing. And you can see here that those inverters, they start responding before frequency, like at the frequency decline right away. So it looks more like inertial response, and it's instantaneous. So they continue testing. I think the plan is to convert it to be grid forming at some point. But currently, as you'll see in the following slides, in Australia, there is no clear application for grid forming inverters, no clear specification either. And so I think many plants, they're just waiting for more clear regulatory framework for them to come up. And so to that point, actually, these are 2 more grid forming projects that they have in the pipeline. This first one in Torrens Island Power Station is going to be the largest in the world grid forming battery, and it's Wärtsilä battery and SMA inverters. It will initially operate in grid following mode, and then is expected to switch over to grid forming. And why is that? Is because they are awaiting regulatory framework and market incentives for grid forming technologies. So this is, again, one of those barriers that I was talking about in the beginning, is where developers would be ready to deploy this technology, but they just don't know what technology is expected to do. And also if there is any revenue flow from providing services. And then another grid forming battery, 50 megawatt, 75 megawatt hours, is being built by Transgrid, and will also be grid forming, will be finished by the end of this year. And it will provide fast frequency response and inertia services in New South Wales network, and it uses Tesla virtual machine mode technology. And so this one, the way it works in Australia, the fast frequency response service, that's commercial service, and somebody will be operating that part of battery. And then inertia service, it's something that transmission network owner can offer to inverter-based resources in the area that have detrimental effect on system strengths in the area. And I'll talk about this more on this slide. So in Australia, Australian energy market operator enforces minimum inertia and system strength requirements in part of the grids, and the most prominent example is South Australia. So that's where grid is weak and a lot of inverter-based resources are connected. And so new inverter-based resources are not allowed to reduce system strengths in the area. And there is also overall minimum requirement for what system strength is supposed to be kept at in the area, as well as inertia requirement. And so they are doing screening and full studies to assess impacts of all proposed projects, and then mitigation measures can be undertaken, such as network upgrades, installation of synchronous condensers, contracting synchronous generation to provide system strengths for those projects, use of grid forming technology that would allow resource to operate at really low system strengths. And this way you can say that it doesn't have effect on system strengths in the area. Converter tuning for existing inverter-based resources could be used, and then some remedial action schemes could be implemented. And so the interconnecting entity, so developer or whoever will own the plant at the end, they are responsible for costs of this implementation. So this got a lot of pushback in Australia because basically with every inverter-based resource in the area, if they are detrimental to system strengths, they were considering to put synchronous condenser next to the plant. And so it was all very inoptimal because they will go just, for synchronous condenser to balance their plant, and then somebody else would build another one close by, and there was no optimization as to where the synchronous condensers are planned. And so there is a new option right now being considered by Australian Energy Market Commission, is where a transmission network owner could come up with solutions to improve grid strengths, and then inverter-based resources in the area, depending on the impact on grid strengths, would pay for this service to transmission provider. And so that would ensure probably more optimal placement of the sources of grid strengths in the area. All right, so this is also a more recent one. IEMO basically seeing advanced grid scale inverters, aka grid forming inverters, as a key for increasing the shares of inverter-based resources. And so as a first step, they developed this white paper on application of advanced grid scale inverters. And it provides recommendations towards enabling this technology to support Australian power system in the future. They define the 4 high-level functionalities that the grid will need in the future from advanced inverter-based resources, and its capability to maintain stable operation in weak grids and provide localized system strengths and support of grid following inverters. And then as the next level, provide inertia and system strengths to support broader power system. And then as the next step, be able of providing island operation capability. And then the next step will be Black Star. So all of these capabilities, they see it as a stepwise, and that they can be implemented maybe more gradually rather than asking for everything at once. And then as one of the recommendations, they recommend prioritizing grid forming capabilities in grid scale battery storage systems. So this is a very important point. And I think, for example, even for areas, I've seen it also highlighted in Hawaii study, and also for, say, area like ERCOT, we have 90 gigawatt of battery storage in the interconnection queue. Normally about maybe 1/3 of interconnection queue ever materializes. But even if that, we can expect, tens of gigawatts of storage in our system in relatively near future, because they don't take such a long time to develop. And because grid forming capability can be enabled on battery storage resources more easily, this is kind of a very short window of opportunity, and maybe some things need to be done right now to incentivize this capability, and so that we can have it in the future, and that would enable more inverter-based resource penetration in some systems. And so the next step for Australian system operator is to investigate how to define voluntary grid forming inverter specifications so that OEMs and developers could deliver these solutions and meet system needs. And so I think they already done first step with that, defining system strengths and inertia requirements, and so they will proceed with that. And so the last few slides I have on national grid approach to kind of exploring what grid forming can do and incentivizing grid forming. So they started with this stability pathfinders. It's currently the first phase is over now, and they're going through second and third phase. So in the first phase, they defined certain locations on the grid where they needed more system strengths, and also they defined additional inertia requirements to that. But as the Pathfinder phase 1 progressed, they decided that there was not enough information available yet about the ability of inverter-based resources to provide the services, and so they limited it to existing technologies. And as a result, they awarded 12 contracts in 7 locations to 5 providers, and they all synchronous condensers. And here you can see the list of requirements. I think in the interest of time, I'll just keep going through that one and jump onto phase 2. So phase 2 was meant to allow inverter-based resources to participate, and that phase was looking for, again, system strengths and inertia provision in parts of Scotland grid. At the same time, in parallel, National Grid had a working group that was working on developing minimum technical specifications, so what they call at the time is virtual synchronous machine. And largely the requirements specified attributes for phase 2 projects were based on this minimal specification from that working group. And these were in addition of phase 1 requirements, and also in addition to existing grid code requirements for inverter-based resources. And so here what they were asking for is for the resource to behave as voltage source behind impedance, to provide inertial power, basically instantaneously, phase jump power instantaneously, and fast fall current injection, and power oscillation damping. This phase attracted, if I remember correctly, more than 1,000 of different options and proposals, and so National Grid had real trouble going through and evaluating all these proposals. It's a little bit delayed because of that, and I think it's expected to conclude by the end of this year, but I'm not quite sure, so don't quote me on that. So that specification for virtual synchronous machines, that one was somebody.
That doesn't matter, just in front of the table, so it's easy to see. Yeah.
Right. So the specification for virtual synchronous machines was later converted into grid code change request, and that's GC 0137. National Grid worked on this for maybe about past year and a half, 2 years. So high level, it's a requirement for grid forming resource to maintain internal voltage source behind reactance, maintain synchronous stability up to 60 degrees phase jump, supply a rock-off response power. So rock-off response power would include inertial response power and type of primary frequency response, or whatever frequency response it's capable of doing. So it's 2 different services here, just merged in one. And it's on top of it supposed to withstand relatively high rate of change of frequency, provide phase jump power damping, fast fault current injection, either one or up to 1.5 per units. There is no requirement to go one way or the other. It will be up to developer to choose. And then control-based real-time and reactive power injection. So that's similar to grid following inverter voltage control and frequency control. Control power with bandwidth less than 5 Hertz, operate in minimum short circuit level, must stably inject current to balanced and unbalanced faults, and the current is supposed to increase with fall of retained voltage. And that's required only up to the inverter capability. They're not required to go into overload. And then they're required to demonstrate these capabilities in simulation tests. And then, so now also Stability Pathfinder phase 3 is starting up. And so that phase, it basically copies the requirement, the latest requirements from this grid code change. And you can, I guess, say that this is the way to incentivize this non-mandatory capability through this phase 3 of Stability Pathfinder. So basically this grid code requirement is going to be non-mandatory, and they were going to come up with the market product that will incentivize it. But I think this phase 3 is kind of the first step in that direction. And you can see here the requirements are basically following this grid code change request. And so for this one, the expression of interest only closes on October 22nd. So this phase just started. They had a webinar on Friday to announce this stage, and so that will be posted shortly, and you can watch the details about this. And so just to wrap up, coming back to my circular problem issue, there is still this kind of disconnect between what grid operator needs and even understanding what grid operator needs, and then translating it to technical specifications for OEM. But even more so, there's no incentive for developer to go for something more than is currently required or incentivized. And so developer is not going to manufacture, not asking for capabilities, grid forming capabilities, whereas system operator could benefit from grid forming capabilities, but there are no defined requirements or technical specifications of what grid forming inverter is supposed to do. And so as a system operator in a system with high shares of inverter-based resources, we need to be looking for interoperability between all resources to prevent instability in interactions in all system conditions. We need solutions for loss of synchronous inertia and frequency support to keep system stable, system restoration and black start, and support during weak grid conditions. Additionally, there is a need for tools and models and planning practices that would allow us to fully identify risks and capabilities of equipment to mitigate those risks. And here, I think it's important to say something maybe I haven't seen, maybe I missed in this review, is how maybe models from this pilot projects, maybe if there are developed models for this project, maybe they could benefit, system operators around the world. If we could test capabilities of these models on our respective system, that could also increase our understanding and speed up the process of developing requirements. And so, say Australian system operator sees it as a first step, and you can see that National Grid is already taking it as a first step. Is a grid code or interconnection requirements that are specifying what is grid forming and what behavior is expected, as well as market mechanisms that could incentivize those behaviors, and they play a critical role in development of this new technology going forward. And then to come into the last point, this requires collaboration between regulators, system operators, equipment owners, and manufacturers to define requirements, mechanisms to deploy this technology, and also to break this chicken egg problem that I keep talking about. And I think this UNIFI project forum is, the best place, and I hope we can progress as the project goes forward. And with that, I'm done. One thing I wanted to mention, I have some extra references here that are somewhat relevant, and I either didn't have time to include here, or they didn't quite fit, but I think they could be relevant as we're working on UNIFI project. Thank you.